All right, hi everyone. I think we're ready to start. So yeah, hello. Thanks so much for it's such a wonderful privilege to be able to present the Aztec protocol. Basically, hi, I'm Zach, and we are a privacy solution for Ethereum. I have to say, it has been an absolutely wonderful conference, and it is so exciting to see so many actual real-world implementations of zero-knowledge cryptography-based applications on Ethereum. I think that one of the key critical things that has to happen for Ethereum to overcome some of its scaling problems in the short and medium term is application-specific, effectively sidechains encoded up as either ZK Snark or ZK Stark based crypto systems, and it is fantastic to see some of that work actually being implemented. It's wonderful to see. So before I start, I just want to make a slight disambiguation between scaling solutions and privacy. Aztec is a privacy provider, so we are enabling confidential transactions, transfers of value on the Ethereum mainnet as a layer 1 solution. And at the moment, we are not focusing on scaling. And so this talk is really about privacy. So yes, I'm just going to go over a little bit about kind of what is Aztec, how does it do what it does, and what are some of the kind of the problems I think our industry faces in actually delivering into the hands of developers and consumers workable, practical privacy on mainnet with the infrastructure that we have today. And then just go over a little bit about our implementation, what our roadmap is, and how to get working with Aztec today, because this is not some kind of theoretical planned solution. This has been working since November. And if you want, you can code up a confidential token using Aztec today and deploy it onto mainnet. So private transactions on Ethereum. It seems like a little bit of an oxymoron. It's kind of like having your cake and eating it. How can we benefit from the consensus guarantees of the public Ethereum network and the liquidity advantages of it being a universal kind of settlements platform, whilst still enjoying privacy that we get either from traditional Web 2 type services or from private blockchains? It seems a little bit impossible, because obviously, if you want every single Ethereum node to validate the integrity of the state of Ethereum's blockchain, and then how on earth do you keep some of that state private and hidden from these validators? So this can be done through the rather esoteric branch of mathematics known as zero-knowledge cryptography. So could I get a show of hands who has heard of zero-knowledge cryptography? Oh, that's fantastic. Yeah, normally 2 people. It's brilliant. So yes, you can use zero-knowledge cryptography for privacy, but there is an enormous gap between the vision and the reality, because Ethereum already today has massive UX problems, I'm sure most of the people here are familiar with. And once you start to add advanced, highly kind of custom bleeding edge cryptography into the mix, then it presents massive problems. They're hard to use. They present difficulties with managing new private keys and new secrets, constructing these proofs, verifying them, broadcasting them. It's really it's a massive challenge. And how do we actually bridge the gap between technical vision and reality? How do we get privacy on mainnet today with the tools that we have and with the technology that we have? And so this is what I think are kind of some building blocks for a confidential ecosystem. If we want confidential digital assets to be a reality on Ethereum, where it is an actual where developers, builders, people in this audience chamber can actually code up confidential digital assets and deploy them as easily as you would deploy any ERC20 token. What has to happen? And I think I'll just go through this list. Basically, I think this is something which is going to become more relevant and more apparent, is that customizable confidential transaction semantics are going to be an absolute necessity for private digital assets. The reason why we're all here, the reason why Ethereum is such a powerful technology, is because its designers did not try and envision all of the potential use cases for Ethereum. Instead, because of our smart contract platform, we, developers, builders, can decide how we can add value using a blockchain. And that flexibility must be extended in the realm of privacy. If I'm building a private version of a token, or like I'm creating like a financial instrument, like a private loan or a bond, I must be able to define my asset semantics, like all the edge cases and extra little bits of logic that I needed to actually for my transactions to be legitimate. I need to be able to customize that in the same way that I can customize an ERC20 token. Confidential assets also need interoperability with one another. It's one thing to be able to create like a private representation of of an asset, of a token, and send that around privately so that nobody can see what was like the value that I'm sending to people or how much I hold. But one of Ethereum's strengths is that a settlements platform. It's the fact that we can settle trades between different counterparties and different assets. Pretty much immediately. And so if you're creating some kind of framework for private digital assets, you also need interoperability. You should be able to build zero-knowledge dApps that can interact with zero-knowledge assets and send them instructions in the same way that you can send an ERC20 token an instruction. And I think that obviously this is relevant, like developer-friendly tooling. Like right now, zero-knowledge cryptography is really, like the barriers to entry are absolutely massive. You have to be extremely literate in this stuff. You have to know the intricacies about how to construct a zero-knowledge proof, about the constraint systems inside how a ZK-SNARK works, and how to minimize the number of constraints. You need to have this enormous corpus of knowledge, which is not sustainable in the medium term or long term, because it massively hinders adoption. I think if Aztec fulfills this mandate, everybody in this audience chamber should be able to, this time next year, be able to very easily, very efficiently spin up confidential assets without having to know anything about cryptography or really how it works under the hood. And finally, you need extremely proof construction and verification. This is more relevant for layer 1 solutions that obviously verifying zero-knowledge cryptography costs a ton of gas. And if your zero-knowledge proofs aren't extremely efficient, then it is quickly unworkable given the throughput constraints of blockchains today. And also, proof construction is a problem. On the small end of the scale, it can present a UX challenge. You have to wait a few seconds to construct a proof and consume gigabytes of RAM. But on the top end, it's like some of the problems that we're experiencing with ZK-SNARKs is that if you want to define any kind of meaningful, complicated piece of logic, the time to actually construct proofs for these SNARK circuits just starts to blow through the roof. And so for private digital assets as a layer 1 solution, you need extremely efficient proof construction and verification, ideally so that you can actually construct these proofs on a hardware wallet. And so with that in mind, those were kind of the considerations that I had when I developed what became the Aztec protocol. A method of basically it's not a general purpose protocol for general purpose computation. It's quite specific. It's for private transactions and for settling private transactions. And so we use some very, very bespoke custom grade cryptography tailored for our specific use case to do this. And the result is that it's extremely efficient to verify and it's extremely efficient to construct these proofs. We use a bespoke encryption function that integrates an extremely efficient range proof. If people familiar with this space will know that kind of range proofs are kind of one of the Achilles heels of zero-knowledge cryptography. If you want to do anything meaningful in a homomorphic crypto system, you need range proofs, and they need to be efficient to verify. Otherwise, your verification costs start to blow up. And the second part of it is that we use zero-knowledge-based Sigma protocols. So these are kind of Sigma protocols are a slightly older tech than a lot of the other zero-knowledge proving systems out there. And yeah, it's kind of fallen a bit out of favor recently. But for the kind of stuff that we're trying to do, prove very simple statements, I want to send Bob or Alice, 50 DAI, and I don't want them to see how much I'm sending. Sigma protocols are extremely efficient. And they work extremely well for what we're doing because they really, I'll go into in a minute, they really promote interoperability between different assets because they don't have different digital assets and zero-knowledge dApps. They don't have problems trusting one another because they don't have to make assumptions about how these assets, their trusted setups will run. And I'll go to that in a bit. Basically, at the core of Aztec, how do we actually enable confidential transactions today is the join split transaction. So this is somewhat similar to how Zcash transfers value confidentially. Essentially, we represent value as UXTO-type objects, like in Bitcoin, not like how Ethereum represents like ownership with balances. The idea being, you can take ERC20 tokens, and through our zero-knowledge protocol, you can convert them into Aztec zero-knowledge notes. And that note will contain an encrypted value, and that value is a claim on the tokens that you deposited. And you can combine these notes around, you can split them up together, make them bigger, make them smaller, and obviously they can have different owners, and that's how you send value. If I want to send somebody, if I have like 100 zero-knowledge DAI and I want to send somebody 50, I take my note, I split it into 2 notes worth 50, and give one to the recipient, and I can prove in zero-knowledge that the sum of the values of the output notes equals the sum of the values of the input notes. It's really basic logic, but that's all you need to make confidential transactions a reality, because if you can make that, if you can prove that balancing relationship, then the smart contract that's verifying the legitimacy of this transaction doesn't need to know what's inside those notes. And that's how we like encrypt value and enable encrypted value transfers. So on-chain, what you see in a note is it has an Ethereum address of its owner. It has a public key and some metadata that can be used by its owner to recover the viewing key and decrypt the note. And the private data is obviously the stuff you don't broadcast to anyone, is the note value, its viewing key, and its spending key. We made a very deliberate choice to split apart viewing and spending keys because it means that you can give viewing keys to people, for example, like institutions like an auditor or a regulator if you need to. You can also give your viewing keys to relayers, third-party services that can construct zero-knowledge proofs on your behalf, but they don't have any kind of privileges or permissions to spend any of the notes that you're giving them the viewing keys to. And so, yeah, that's our fundamentally like the crux of how we represent value and how we transfer it around. We just to make something like unambiguously clear, what Aztec does is it enables me to send somebody some value where nobody knows what's like the actual values being transferred, and ownership values are encrypted. The owners of Aztec notes is not hidden, and the existence of an Aztec note is not hidden. So we did this very deliberately to promote interoperability between different assets. It makes it a lot easier to create like a confidential token standard where like multiple confidential tokens can actually interact with one another, because if the notes are kind of in the clear, like if these contracts actually know about the existence of other notes, then it makes it a lot easier to validate the logic. We also add anonymity into the Aztec protocol by using a stealth address protocol. I think it was originally developed by Monero. Effectively, using a stealth address wallet, you can generate accounts, Ethereum addresses, and accounts that are completely unlinkable or untraceable to any other like on-chain identity. And if I want to send somebody some value confidentially, and I know that person has a stealth wallet, I can use the kind of the public keys from that wallet to, for them, in a non-interactive manner, derive an Ethereum account that only they have the private key for. And so that's how we add anonymity into Aztec. So this is some mathematics. Basically, I want to very briefly go into some of the mathematics behind how Aztec does the stuff that it does. And so I apologize so much in advance to some people if this gets a little bit too esoteric, but I think it's quite important because what we claim is quite a big thing. Basically, we have an extremely efficient range proof. The whole reason why Aztec is efficient to verify is because of this magical range proof. How the hell do we have an efficient range proof? This has been kind of something that's been intensely sought after for a while. And traditional ways of doing a range proof, like proving that your number is smaller than another number, is you decompose your number into bits. Basically, if you want a 32-bit number, you have 32 like encrypted representations of bits, and you send a zero-knowledge proof that every single bit is either 1 or 0. And then you combine them all together. And there are like multiple ways of making this a lot more efficient. Bullet proofs is one of them, which makes where the proof size is logarithmic. But it's still an extremely like computationally intensive thing to do. So how do we actually create range proofs? Well, the answer to that is we don't. We create lazy range proofs. Effectively, when you send an Aztec transaction that requires a range proof, you don't prove that you have satisfied, like that a number that you have is within the relevant range. What you do is you prove that somebody else has already validated that. Effectively, we have a trusted setup where a set of signatures are created. These are called Bonin-Boyer signatures, where Y is the trusted set of toxic waste, and this K value here is the kind of one of the integers that is tolerated within our range. So you have one signature per integer in the range, and you can use these signatures to create commitments, like a Pedersen commitment, like a basic it's a basic encryption function where you can encrypt an integer, and very easily prove that whatever integer you have, it was signed by the trusted setup. And so basically, what we can do with that is there are a lot of Sigma protocols out there, like zero-knowledge proofs, that prove really interesting relationships that are quite useful. But the problem is they all don't have range proofs, and therefore they're kind of useless for Ethereum's purposes. But you can basically take these Sigma protocols as they are, don't do anything else with them, and basically just tack on this little extra step using our asset commitment function and validate any range proof you want. So you know what? Maybe that's a little bit too. I'll go back to this later if people want to go through it. We spent a lot of time trying to develop a zero-knowledge protocol that was tailored for the current weaknesses of Ethereum. This commitment function, these range proofs, this entire zero-knowledge protocol that we put together was designed specifically for Ethereum, for the limitations that we have. How can we make a proof extremely efficient to verify? And then how can we actually give people that customizability I mentioned at the start? This whole customizable confidential transaction semantics. So I just talked about this thing called the join split transaction. But that doesn't look very customizable. It's not very custom. But the thing about Sigma protocols is, I mentioned that trusted setup at the start, but you can create a multitude of Sigma protocols that prove different things. Like they can have niche logic that you might need for certain kinds of assets. So for example, you might want to have traders prove that they own less than 10% of the asset's total supply for regulatory reasons. You might have an interest-bearing asset that yields 3% per quarter, and you need to give your consumers a way of claiming that interest in zero knowledge so they don't reveal their holdings. These are all zero-knowledge proofs, custom, bespoke zero-knowledge proofs that we've created specifically for the kind of statements that you need when dealing with financial instruments and financial assets. And the valuable thing about a Sigma protocol, like what we're doing with them, is you don't need to perform any other additional and extra trusted setups. You can continuously add and develop extra proofs that prove more elaborate and more interesting and more niche statements depending on what use cases arrive, and you don't need to do any kind of extra work with the setup, which means that you don't have any problems with having to get existing consumers to trust if you want to extend the protocol, you don't need to kind of ask your consumers to trust you as you perform another trusted setup, or you generate some other extra secrets. And it's this flexibility and extensibility which I think makes the asset protocol so quite useful today. Because these statements aren't particularly expressive, because it's all just basically around value transfer. They're quite simple. They're really efficient to construct proofs. So I haven't actually run any benchmarks because the proof construction is on the order of milliseconds. It's really not been relevant. And similarly, proof verification is extraordinarily efficient. It costs, at the moment, today, with current gas schedules, it costs about 800,000 gas to verify an Aztec confidential transfer. So if you want to use the asset protocol to send somebody some value confidentially, it'll run you 800,000 gas, which is enormously efficient when compared to some of the other ways of creating this kind of system. And with planned protocol upgrades coming in the near future, hopefully, with some EIPs to reduce the costs of these pre-compiled smart contracts, that'll drop to about 200,000 gas. And then that's actually really starts to become something that can be used on quite a regular basis for a very large number of use cases. And I think that is what is so powerful about private transactions in general, is that once the gas costs for performing these kinds of transactions falls below a threshold where they can be commonplace, then it enables an enormous number of use cases on Ethereum that currently can't exist because you can't be competitive with traditional financial systems where people expect privacy by default if you can't provide privacy. So this is kind of how it all fits together. Imagine you have some ERC20 tokens, you want to convert them into notes. You use our interfaces and our APIs to construct some Aztec zero-knowledge notes that are equal to the amount of tokens you're binding. And then you construct this join split transaction, where basically you say, hey, look, I have some output notes and I have some input tokens, and I want to prove to you that these output notes equal the sum of the output notes equal the tokens I'm putting in. The more you can also add extra notes into these kind of transactions if you already have some, which helps to obfuscate things and add greater privacy and kind of complicate the transaction graph. Obviously, this does reveal a bit of information. Everybody can see what you're putting in. They just can't see what you're getting out. And so once you actually, the privacy benefits that you enjoy start to multiply significantly once you actually start trading and transferring notes inside the crypto system. And then, yeah, if you want to send somebody some value, you just assign another user to own one of these notes. You have a secret sharing protocol, which means you can very easily construct viewing keys for these people for these people without having to actually transfer any secrets around. And yeah, this should probably be in appendix. I'll go into it in a bit. But basically, if you actually, this is if you actually want to use this stuff, we have some local JavaScript libraries that you can run to actually construct these proofs, and a list of deployed smart contracts which you can use to actually perform the verification of this stuff. This is all culminating in what we're calling the Aztec Cryptography Engine. So private transactions in general, like I've talked about modular proofs and being able to use different zero-knowledge protocols, blah, blah, blah. But how does this all fit together? Because like if somebody here wants to create like a zero-knowledge version of an ERC20 token, they shouldn't have to be intimately familiar with like modular proof construction or any of this nonsense. So what we are creating is this Aztec Cryptography Engine. It is a suite of smart contracts whose job it is to validate our family of zero-knowledge proofs and essentially convert zero-knowledge proofs into instructions for digital assets that subscribe to the cryptography engine. So if you give this a proof to validate, it'll say, okay, yes, this proof is valid. You need to destroy these notes. You need to make these notes, and you need to probably emit this event. And here you go. And so this is kind of the version 1 of our proof family. We have a lot more on the boil, but we kind of want to focus on the core stuff first to just get this out into production. The basic join split transaction, a bilateral swap if you want to do trading between two different zero-knowledge assets. A dividend computation if you want to validate that like one note is a percentage of another note for interest payments or things like that. And then some range proofs because they're really efficient and cheap to do using Aztec, and they're quite useful for a multitude of reasons. You might want to add some range proofs for some custom logic that you have in your smart contract. And so the idea is using that you don't have to know what goes on under the hood for these inside these proofs. You can just use them. You can use your interface and go, okay, if I'm building some kind of weird confidential asset with some custom stuff, I need a join split transaction, and then on top of that, I want dividend computations, and I want maybe some range proofs. And then it's constructing interfaces to actually like validate all of this is extremely easy because you don't have to understand anything about what's actually going on inside under the hood. That's the logic, at least. And so this is all culminated in ERC 1724. This is our confidential token standard for zero-knowledge assets. It has an ERC20-like interface, so hopefully it should be, we designed it purposefully to be quite like familiar and intuitive to developers. And if you construct an ERC 1724 asset, then according to this interface, it's compatible with all the other ERC 24 assets. And so if you have some zero-knowledge dApps that interface with the standard, then your token will by default be compatible, just like with the ERC20 tokens. And so, hang on, this thing has a laser pointer, doesn't it? Ooh, how do I, I'm going to turn things off if I, hey. Yeah. So the kind of the crux of what's going on here is this confidential transfer method and this confidential transfer from method. You can see we've kind of deliberately abstracted away all the zero-knowledge proof stuff. It's just one bytes argument that our APIs will construct for you. And it's this method, confidential transfer from, which is not, I think, apparent. It's not intuitively apparent, I think, why that method is so valuable, because normally with a zero-knowledge proof, they have to obviously be custom-made by humans because they require knowledge of secrets. However, it is absolutely imperative, I think, for any kind of system of confidential settlements that other smart contracts can trigger transfers on behalf of users. I mean, one simple example would be an escrow account. that only enacts a trade if certain conditions are met. Another one would be a decentralized confidential exchange that only fulfills orders if certain conditions have been met. And so by providing this interface, we actually enable other smart contracts to do that. Zero-knowledge dApps on Ethereum today. And we're trying to create an ecosystem of dApps. Basically, it's focused around constructing private digital assets that can all trade with one another, that will understand each other's kind of like the zero-knowledge proofs that are going on, and that they all subscribe to the same cryptography engine to validate their zero-knowledge proofs. And this is really the crux of why this system is workable on Ethereum, on mainnet today. And that's because all of these dApps and all these assets that are all using, that all require the like a ton of zero-knowledge proofs, they all query the same engine to validate proofs. And so this is important because a lot of zero-knowledge proofs that we have are kind of supersets of other proofs. So imagine that zero-knowledge dApp is a confidential decentralized exchange. It needs, using our bilateral swap proofs, it can validate that an order it's received is legitimate. It then needs to send confidential instructions to the two assets it's trading. It says, you need to make these notes and destroy these other notes. Get to it, please. But these assets, they have no clue about that ZK dApp contract. They can't trust it. If this thing gives them an instruction, how do they know it's legitimate? So normally, those assets, those ZK ERC20s, would have to they would require their own zero-knowledge proof, to validate their own transaction semantics. And so to have this network of one zero-knowledge dApp issuing like a trade against two assets, you would need to validate 3 zero-knowledge proofs. And traditionally, that could very easily blow you through the block glass limit. However, the cryptography engine knows full well that that bilateral swap proof I mentioned already satisfies the kind of the balancing relationships that are required inside the join split type transaction. And so if these ZK ERC20 contracts, they can query this engine and go, hey, I was given an instruction by this dApp. It says it validated this weird proof. Is this instruction legitimate? And the cryptography engine can just go, yes, it is. I validated it. Get to it. And you don't need to perform any additional redundant computation. And it's this kind of sharing of relevant zero-knowledge proofs which makes us so efficient. This kind of trading system where a transaction could easily normally blow you through the block gas limit if you wanted to do this all in zero knowledge, this costs about 800,000 gas for this entire interaction, at least in the context of validation of the cryptography, not for changing state variables. But that's exceptionally efficient, and that means it's workable today. And so this is culminated into 2 EIPs, that one I mentioned before with the confidential asset, and another one, which is just the specification for our cryptography engine. Because our cryptography engine that we've developed, it uses Aztec notes, but we've tried to make it quite generic. So if you want to use other kind of zero-knowledge proving mechanisms to make a cryptography engine, you can. It's just that we picked Aztec because for our purposes, it's the most efficient. And so this is not some planned, imagined future technology. It's working today. We deployed a zero-knowledge version of the DAI token in November and started trading it around confidentially. And we've been kind of iterating and developing it ever since. Right now, our focus is on providing the high-quality tooling and resources that developers need to actually make confidential tokens. And so, yes, we have a kind of a media, some blog posts written by my colleague Paul on actually how to actually today build a confidential token on Ethereum using our technology. So you can do that right now if you want to. We're also partnering with some other protocol providers and developers. So partnering with Republic Protocol to help settle their trades in their dark pool. I think this is going to become more of a relevant problem. If you're building some kind of sidechain or scaling solution that values privacy, that has privacy integrated inside of it, well, what happens when you need to resolve your trades with the mainnet? Because the mainnet is going to be the ultimate record of value. If that's all public, then you aren't a privacy-preserving solution. And so, however, what we enable is that you can settle confidential trades and confidential interactions happening within some kind of side chain or dark pool. You can settle them confidentially on mainnet with Aztec and enable your private little side chain to extend its privacy guarantees to mainnet. So this is all culminating in our Aztec monorepo. So the packages that we have there are all published as NPM modules, so Aztec.js for our JavaScript proof construction libraries, and our protocol module for templates of smart contracts, so templates of ZK ERC20 tokens that can be used to create confidential assets. And so yeah, that's kind of the state of play at the moment. This is our roadmap for version 1.0, the full release of Aztec. What's really on our plate at the moment is we want to release our MVP cryptography engine with all the bells and whistles thrown onto it, and the complete our complete proof construction API. Now we've integrated 3 proofs. We have a couple more we want to add in before we consider that ready. We also are implementing our trusted setup multi-party computation. So I mentioned before we do have a trusted setup. However, it's extremely similar to Zcash. And that powers of Tau ceremony, where it can have multiple participants, and if any, like hundreds of participants, it can scale indefinitely, and if any one participant acts honestly, if only one of them acts honestly and destroys their toxic waste, then the entire protocol is secure under conventional discrete logarithm assumptions. And so this trusted setup is actually, it's so similar to Zcash that it's like we require the same trusted setup that ZK-SNARK-based solutions on Ethereum require. So I think there's the, this is all like this multi-party computation is already kind of being in the works from other protocol providers, and it's something that we'd like to get involved in. And also form of verification of our smart contracts. I think if there's a need or a use case for form of verification, this would be it. This is highly custom bespoke zero-knowledge cryptography. And we've formally proven mathematically that the protocols are sound, so you can't fake a proof. But we also want to extend that guarantee to prove that our code is a faithful expression of the mathematics that we've created. And then we're slated for a production-grade release in Q3. We do need our trusted setup finished before we can really move into production and actually tell people, yes, you can use this on, like all of this on mainnet today. We have our ecosystem deployed onto testnets if you want to actually start developing this stuff and working with it. And then we want to focus quite heavily on integrations and zero-knowledge wallets. One final thing, sorry, I know it's been quite a long, actually how long has it been? Sorry, 1 second. Yeah. We have, one of the focuses of Aztec has been, well, we want Aztec working today. There are a lot of planned and slated protocol improvements to Ethereum that will make our work a lot easier. That will make zero-knowledge cryptography a lot easier. But as developers on top of Ethereum, we have limited agency over how quickly those improvements get integrated into the protocol, and so we want to focus on what can we do today to make this all faster, to make this all cheaper. And so one of our side projects is accommodating in something we call VS-Strudel, because it performs elliptic curve arithmetic on short Weierstrass curves, specifically the ZK-SNARK curve supported by the precompiles. This is a smart contract. But it is quite substantially more gas efficient than the pre-compiled smart contract you normally traditionally have to use for elliptic curve multiplication. So it's going to reduce our verification cost by 20%, but any kind of crypto system that uses that curve can benefit from this. And so we plan to kind of roll this out a bit more and distribute it a bit more widely. So that's really it for my presentation. Thank you so much for listening, and it's been a real pleasure. Very happy to answer any questions.
Yeah, thank you very much for your talk. Can you compare your computational transactions decision with other ways to do this? For example, that do Starkware or with the Starks and something.
Yeah, of course. So what we wanted to focus on with Aztec was crushing down the cost of verifying an individual zero-knowledge proof, because a lot of other solutions, so for example, Starkware and ZK-SNARK-based solutions, they are most best suited for validating a large batch of transactions. With ZK-SNARKs, you have one issue is with ZK-SNARKs you have a trusted setup involved, but unless you use a Sonic-style ZK-SNARK, you need one different. If you have customizable semantics, you need one setup for each asset, and then they all can't really intuitively trust each other, and you can't have that kind of cryptography engine construct which will validate a set of proofs and have assets that can intuitively trust those proofs. So that's why we couldn't really use ZK-SNARK as it stands, and Sonic, straight up wasn't around when we developed this, and it's also, again, it's much better for batch validation of transactions because it's quite expensive to validate a single proof. Similarly with Starks, the size of a Stark proof is logarithmic with the number of constraints in a Stark circuit, so you wouldn't want to use a ZK-SNARK to validate a single proof. The reason we didn't focus on batch validation was because we wanted those customizable semantics. We wanted people to be able to adjust like what they considered to be a valid transfer for their confidential assets, and so we couldn't use batch validation techniques. The other alternatives were bulletproofs, which has been implemented by Dan Nabona's team, I think, and people behind Zeta. We chose not to use bulletproofs just purely because of verification costs. Bulletproofs are the size of a bulletproof is logarithmic with the amount of kind of complexity in its proof statement, but the amount of computation you still have to do is linear. And so, if you want to validate a bulletproof range proof over a 32-bit integer, I think I might be wrong on some statistics, some of the numbers here, but I think it costs about 64 scalar multiplications. There are some ways of speeding that up, but ultimately, it's always going to be like for Ethereum as it is today. That's always going to be a bit too expensive, and so. Yeah, that's kind of, I think that's a bit of an overview.
Thank you.
Well, thank you very much for this brilliant presentation. I really appreciate it. So my question is, well, if I understood well, Aztec are now intended to be like generic ZKPs. They are for.
Sorry, my hearing's not very good. Could you speak up a bit?
Do you hear me now?
Yeah.
Well, Aztec are not intended to be like generic ZKPs, not for arithmetic circuits. They are more usable for range proofs. So, for example, the confidential transactions, where there was, for example, the Greg Maxwell range proof, but this used like ring signatures and then Pedersen commitment for every bit, and then there is the bulletproof. My question is, in terms of verification, how do you compare the bulletproof and the Aztec for the confidential transaction protocol, like the one used in Mimblewimble or in Monero, as you have mentioned? And for Monero as well, so they are using confidential transaction as well with state address, so you're doing pretty much the same. So would it be interesting to change the range proof in Monero, in EthCC Monero with the Aztec? So this is my first question. And my second question is, well, you are leveraging on Bonnet-Boyen signatures. So what happens when, if we can take a look at the...
Yeah. Yep, something here.
Yep. So the k is the integer you want to hide. So what happens if the k is equal to the secret y? So this one is 1 out of 0 now. What happens if k is equal to y? Y is your trusted setup, your secret, and k is the one you hide. So in Bonnet-Boyen signature, for example, they change the signature with the secret element. But in this case, it will create a vulnerability because you have to check if k is equal to y, and y is the secret key in your trusted setup. So doesn't this make any vulnerability, like branch prediction?
So I'm going to start in reverse order because you might have to ask some of the other questions again because I think I've forgotten them. But in terms of like the vulnerability of what is k as y, if y, we use a zero knowledge proof to basically, if you want to commit to an Aztec node, you have to create a zero knowledge commitment to k. You need to know what it is, essentially, and so. Because y is ideally, y is a trusted subtoxic, so it has to be destroyed for this protocol to be secure. So you shouldn't be able to create one of these Aztec commitment tuples where k is y, because you won't be able to provide the zero knowledge proof that opens this commitment to y.
But what happens if the k turns out to be the y?
That's what I'm saying. Like you have to commit to k. So what I haven't actually, hang on.
So you're comparing the commitment. You're
One
comparing
second.
Pedersen commitment.
Oh yeah, here we go. So imagine you have. Oh yeah. So this is your Aztec commitments. You have two commitments. You have this kind of elliptic cut point gamma and sigma, and you have these scalars k and a. So what is equal to y? Well, the very first step of the Aztec zero knowledge proof is you need to, the first proof statement is, I know a value k, a scalar, an integer k that opens to this commitment. You basically have to, it's like a Schnorr signature of knowledge. Basically, you commit a blinding scalar. So first of all, you generate some random scalars. So call them bk and ba for blinding scalars. So they are just random integers in the prime field of this elliptic curve. And then you commit your blindness scalar, which is going to be this gamma to the BK, H to the BA. Step 1. Actually, is there a board eraser? Oh dear, there's not. Okay, never mind. So basically, it's like a Segwit protocol is like a 3-step proof. The first one is you kind of commit your blindness scalar. You then create a challenge variable, which is going to be a hash. So H, I just stand for hash function. We use kecactu56 of your commitments. So sorry, gamma, sigma, and this blinding factor. Oh, thank you. So this running out of space already. So basically, you create this challenge variable using the Fiat-Schmidt heuristic. If you're going to use this as an interactive protocol, the challenge variable would be random. And then what you have to do is you have to create effectively signatures for K and A. So you create a representation of K multiplied by C, plus the blinding scalar, and then for A as well. And you have to, what you do in Aztec is you validate as step 1 of the zero knowledge proof is the verification smart contract checks that you've created an accurate commitment to K. So what it's going to do is it's going to validate, it's going to compute this gamma to the K bar with H to the A bar, and then kind of divide this by that sigma coordinates expatiated by the challenge variable. And that should be equal to the blinding scalar, to the blinding factor. And what the smart contract will then do is it will then compute that challenge variable itself using the blinding scalar that is recovered. And if you have not faithfully made a commitment to that scalar K, then that blinding scalar will not equal the original blinding scalar, blinding factor, and that the hashes won't match. And so effectively, step 1 of an ASIC proof is you have to prove I know a scalar K that is equal to some integer. And you cannot do this if K is equal to Y, because you do not know what Y is. And so that's how we avoid a situation of a malicious prover trying to commit to to the setup KY and break the Bonan bias signature.
Okay, well, I've got a little bit lost in the notations, but I would be very happy if we can take some time to discuss this more in details.
Yeah, sure.
And regarding the Weierstrudel, the smart contract, is it working now for the edges cases? Like when you add in points at the infinity, or when you are doing...
So sorry, what was that?
When you are adding points at the infinity, for example, if you are using a Weierstrass curve, so the point is in the projective coordinate, so does it work in with Weierstrudel? So, because last time I saw the GitHub, it wasn't working with the case edges.
Sorry, my hearing's really not very good. I think you're saying, does Weierstrudel work with points of infinity? No, not yet. We don't use Weierstrudel to validate our proofs yet. Kind of, that's more of a side project. Like, when we have time, we'll get it ready.
Well, thank you very much, and it would be a pleasure if we can talk this more in detail. Yeah.
Thank you very much.